In this video, I'll be solving example 5.3. I'm going to pause to read. And essentially, we have this hanging mass M that is being supported by the uniform magnetic field and the current, which produces some magnetic force upwards. And we have the gravitational force downwards, and we want to find at what current in the loop would the magnetic force exactly balance the gravitational force downwards. I've also brought in figure 5.10 here, and they've sort of already demonstrated that the current must go clockwise in order to produce this magnetic field upwards, or sorry, this magnetic force upwards. So I've brought over a couple pieces of information here. B is into the page, and the magnetic force is, this is just a general definition for the magnetic force. And so I'm going to simplify this equation on the right here and change it into like a kind of magnitude of the force by using this definition of the cross product. We have dl times b times sine theta, where theta is the angle between b and dl. And so like I said previously, b is into the page. And if I look at the figure here, we'll have like a dl segment here, dl segment here, maybe a dl segment here. And therefore, at each of these dl's on the wire, theta is equal to 90 degrees. And therefore, sine theta is going to equal to 1. So if I simplify this down a little bit, we have I up front because it is constant, and we have b up front because it is constant. And the integral of dl would just be L, where L is the length of the wire that is within the shaded region, the uniform magnetic field. So now if I were to use the right-hand rule to now find the direction of these magnetic forces in each of these segments, you'll see that we get a magnetic force upwards on this top segment, we get a force to the right, and we get a force to the left on the left segment. And you'll also notice that on these vertical segments of the wire here, we have a similar value for L. Or I shouldn't call that L, right? So maybe we call this B, where, these vertical segments, L is equal to B. And so by our definition of the magnitude of the magnetic field, or magnetic force, these segments are going to kind of counteract each other, and these forces are going to cancel. So we're just left with this force upwards due to the top segment. So now let's solve for the force on the loop, since we know that our net force is going to be due to the top segment. We could just solve for that using our equation here. And we have I times B times the length of the segment, which is A. That is our magnetic force. And we also have this gravitational force, which of course is equal to mg. And we want to balance out these forces. So this is our upwards force. This is our downwards force. Now let's set them equal. And we could solve for current. You'll find that the current has to equal mg over b times A. Now, in this example, Griffith introduces this idea, what if we increase the current? Well, in that case, the force upwards on the loop is going to be greater than the force downwards due to the gravitational force. And so one may be tempted to write that there's work done by this magnetic force. Let's say that the mass moves some length h. And so we'll have this evaluation where the work is done by the magnetic field. Well, this is preposterous. This is not true. We know that the magnetic force all magnetic forces don't do work. And why is that? I think this is easiest to explain with a single point charge. So I'm going to give that example. And for a point charge, we have this definition for the magnetic force. I'll write it down real quick. And so when the charges are moving, or when the loop is forced upwards, we have now this velocity up and horizontally, right? We have this is our point charge Q. We have a horizontal component, which I'll denote as W, where it's related to the current like this. And we have this vertical component, U, that is the kind of vertical velocity that we're moving. And by definition, by this cross product, the magnetic force is always going to be perpendicular, right? This is V. The magnetic force is always going to be perpendicular to the displacement vector V. I'm going to write that down real quick. And this is the displacement of the charge, right? So therefore, there is no work being done by B, by the magnetic field, because it is perpendicular to the displacement. Instead, it's more accurate to write that the work is being done by, let's say, like it's just a generator or a battery, whatever is producing this current is going to be what's doing the work on the loop. And therefore, we have work due to the battery would be accurate here. So that's the key here. Since the magnetic force is perpendicular to the displacement, there is no work being done by the magnetic field, or magnetic force, excuse me. No, that is not right. By the magnetic force. I don't know why I wrote B here. My bad. Because that is going to be perpendicular to V. Hope that makes, hope that's clear. Anyway, thank you.